All right, let's dive right in. Today, we are going back to square one, the absolute bedrock of all geometry. We're talking about points, lines, and planes. And trust me, this isn't just a vocab list. This is the DNA for everything, and I mean everything, that comes next.
But let's kick things off with a kind of mind-bending question. How in the world can you build a system as logical and precise as geometry using ideas that you can't even formally define? It sounds like a total contradiction, doesn't it? But that's exactly where the beauty of this whole system starts.
You see, these first few concepts aren't just things to memorize for a test. A better way to think about them is as the fundamental rules of the game. Every proof you write, every theorem you learn, every single problem you solve, it all gets built right on top of the foundation we're laying down today.
So, to answer that big question from before, in any logical system, you have to start somewhere. You've got to have a few core ideas that we all just get, intuitively. We don't define them with other words, we just agree on what they are. In geometry, there are exactly three of these.
First up, the point. Now, a point is not the little dot we draw on the paper. That dot is just a symbol. A real geometric point is a perfect, exact location in space. It has no length, no width, no depth. It has 0 dimensions. It's just there. And we name it with a capital letter, like point A.
Next, we've got the line. Imagine a perfectly straight path that has absolutely no thickness. And, this is the key part, it extends forever in both directions. It never, ever stops. Those little arrows we draw on the ends, that's what they signify. We can name a line using any 2 points on it, say line AB, or sometimes with a single lowercase letter, like line M.
And number 3, our last undefined term, is the plane. The best way to picture a plane is to think of a perfectly flat sheet of paper that goes on forever in every direction, up, down, left, and right. It has length and width, but 0 thickness. We can name a plane with a capital letter, like plane P, or by picking any 3 points on it, with one important rule: they can't all be on the same single line.
Okay, so that idea I just mentioned is super important. Let's lock it down. When points are collinear, it literally means they are collinear, or together on the same line. Simple enough, right? And it's the same idea for coplanar. Those are points or lines that all lie on the same plane. So when we say non-collinear, it just means the points don't all line up perfectly.
Okay, there we have it. Our 3 basic building blocks: the point, the line, and the plane. Now the real fun begins. We can start using these simple, intuitive ideas to build more complex terms with total precision. Let's start with a line segment. If a line goes on forever, a segment is just a piece of it. It's a chunk that's been cut out. It has 2 specific endpoints, and because of that, it has a measurable length. It's finite. We name it by its 2 endpoints, like segment AB.
And next up is the ray. Now listen closely, because this is where a lot of people make a simple mistake. With a ray, the name is everything. Think of a ray of sunlight. It starts at a specific point, the sun, and then shoots off in one direction forever. When you name a ray, the first letter you write must be the endpoint where it starts. So ray AB starts at point A and goes on forever through point B.
This little chart here just lays it all out perfectly. A line, no endpoints, infinite. A segment, 2 endpoints, finite. A ray, 1 endpoint and infinite in just one direction. But look at that last row. That's the one to remember. For lines and segments, you can call it AB or BA. Who cares? It's the same thing. But for a ray, the order is absolutely critical. Ray AB and ray BA are 2 totally different things, pointing in opposite directions.
So let's do a quick check. A student needs to name a ray that starts at C and goes through D. They write down ray DC. Is that right? Think about it for a sec. No, it's totally wrong. Remember the rule. Endpoint always comes first. The only correct name is ray CD. This is probably one of the most common mistakes, so burn that rule into your brain.
Okay, we've got the definitions, we've got the rules, but geometry isn't just about memorizing words. The real power kicks in when we connect these ideas to algebra and start solving some real problems. Let's see how it's done.
The main tool we're going to use is called the segment addition postulate. And you know what? It's as easy as it sounds. All it says is that if you have a point sitting on a line segment between the 2 ends, then the length of the first part plus the length of the second part has to equal the length of the whole thing. Part plus part equals whole. That's it.
So let's put that to work. Here's our problem. We've got 3 points, x, y, and z, all on the same line.
We're told y is between x and z. The total length from x all the way to z is 18. The first piece, xy, has a length of 2t plus 1, and the second piece, yz, is t plus 5. Our mission is to first find the value of t and then use it to find the actual length of segment xy.
Okay, let's walk through this together. Step 1 is the setup, using our postulate. Part plus part equals whole. So, xy plus yz equals xz. Easy. Step 2, we substitute in the algebra we were given. That gives us 2t plus 1 plus t plus 5 equals 18. Now for step 3, we just solve for t. Let's combine our like terms. We've got a 2t and a t, that makes 3t, and we have a 1 and a 5, that's 6. So, 3t plus 6 equals 18. Subtract 6 from both sides, we get 3t equals 12. Divide by 3 and boom, t equals 4. Now, warning, don't stop here. This is a huge trap. The question also asked for the length of xy. So for step 4, we have to plug that 4 back in. xy equals 2 times 4, which is 8, plus 1, which is 9. And for the last step, step 5, we can quickly verify our work. If t is 4, then yz is 4 plus 5, which is also 9. Does our first part, 9, plus our second part, 9, equal the whole thing, 18? Yes, it does. We nailed it.
That problem shows just how critical it is to be precise and to follow the rules. So let's make sure all this stuff really sticks by going over a couple more key rules and the common traps you want to avoid.
Here's a little brain teaser for you. Let's say you have two different lines, and they both happen to pass through the same single point, P. Does that mean they have to be the same line? The answer is no, of course not. Just think about the spokes of a bike wheel. You can have tons of different lines all passing through that one single point in the center. They just intersect there.
And that actually leads to some of these core rules, or postulates, that you just got to know. The first is huge. Through any 2 points, there is exactly one line you can draw. We've already mastered the segment addition postulate, and just so you know, the same idea works for angles. And finally, a cool one. When 2 planes intersect, like the wall and the floor in a room, they meet at exactly one line.
So, let's put it all together. Here is your official checklist for success. 1. Never ever flip the name of a ray. 2. Always know the difference between an infinite line and a finite segment. 3. Don't just assume points are in a straight line unless the problem specifically says so. And 4. The big one we just saw, always finish the problem. Don't just solve for t and call it a day. Go back and find the length or the measure you were actually asked for.
So, after all this, what's the big takeaway? What's the point of it all? It's really about developing the right mindset. It's about learning to think in a way that values structure, logic, and above all, exactness.
And that really brings us to the most important thing I can tell you today. It's this: precision is the whole game in geometry. The tiny difference between a line and a ray, or getting the order of the letters right, that's not a small detail. That is the detail. Getting these fundamentals perfect right from the start is your ticket to understanding everything else.
So now you have them. You've got the language, you've got the rules, you've got the fundamental building blocks of this entire logical universe. The only question left is, what are you going to build?